Hi, this is Group 6, and this is Presentation 1 for Programming Assignment 4, Premium Theory Version 2. We will be talking about Haskell standard classes and monads based on information from GIH Chapters 8 and 9. Haskell types serve as fundamental units for Haskell in providing type-safe functionality. We are going to talk about class features and class creation. Standard type classes in Haskell are part of the Haskell library. The examples we will talk about in this presentation are EQ, ORD, enum, show, read, and bounded. We are also going to talk about functors, applicatives, and monoids. Lastly, we will cover monads, which are frequently encountered in Haskell. Some core libraries, like I/O, are built upon these concepts. Now, onto types in Haskell. One of the biggest parts in Haskell's existence is the type system. Haskell is strongly and statically typed, meaning each type in the language is checked against each function at compile time. This means any type-related errors that could happen at runtime would be found during compile time. Types are invariant in Haskell. That means that once they are declared, they remain constant during execution. Types are often referred to as documentation or clarification, as they can provide a lot of insight into what a function actually does. Type inference. Similar to Python, the type does not need to be set. Instead, the type can be gathered from the context and set automatically instead of manually. Parametric polymorphism. Haskell has the ability to have functions that work regardless of the types of parameters that have been inputted. This gives us the opportunity to tweak just the type declaration a little bit to change the functionality altogether. Behavior orientation. Types in Haskell are based on how they behave. For example, a class is of the equals type will have two instances of that class that could possibly be equated using a double equals sign. As described on the last slide, parametric polymorphism is defining classes without explicitly stating what classes they are intended for. This allows us to say, make up a class that could make both a tree of ints and one of strings using the same function. This allows us to define broadly at top level and then extend or inherit more specific functionality from the class types they can be labeled as later. An example would be anything labeled as a member of the equals class is able to be compared in that fashion. Ad hoc polymorphism, on the other hand, is basically any polymorphism that isn't for parameters. Container types. We have the ability to take types and put them inside of other types using type signatures, as seen in the entity example on the right. Entity contains the type float. Type contexts are prerequisites for what types are going to be allowed in that class type. Type constructors. These are the modifiers showing what type is being created. In the list example, list is the type constructor for L. Algebraic types. This is a type that takes parameters. An example of this would be a function. Concrete types, on the other hand, don't take parameters. An example of these would be something like an int or a string. When defining a type, there are three usual ways to start the statement: type, new type, and data. Type makes a synonym. Starting a declaration with type makes that class type you have defined the same as the type after the equals sign. New type is when you want to make a new version of an old class that duplicates the way that that class handles a single parameter instead of duplicating the entirety of a class. Data is when you want to make an entirely new class with no overhead at all. You'd be starting from scratch. Please proceed to our next video, where we will start with standard Haskell classes.